My work is done in collaboration with Benoit Cerruti, Greg Werner, and Mitch Bigelman. All of these people are at the University of Colorado. Okay. Before we get into astrophysics, I just would like to lay out some terms and define what we mean by, or at least what I mean by, particle acceleration. I think it is kind of the accepted view that when we say particle acceleration in astrophysics, what we mean is some efficient production of non-thermal particles, high-energy non-thermal particles, by some sort of energy release process. And the point here is that we want to produce, let's say, a power law extending up to energies that are significantly higher than the average dissipated energy per particle. So let's say, for example, in the case of reconnection, if we have some magnetic energy, such as in the solar flare, we somehow get rid of it. It gets converted to particle kinetic energy. There is an average energy, dissipated energy per particle that we can define. Accelerating particles up to that energy, I think we can just call heating. It's not non-thermal particle acceleration, in my view, it's just heating. The interesting questions, the questions of particle accelerations, are the questions of whether we can produce substantial number of particles with energies much higher than the average dissipated energy per particle. For example, in the case of solar flares, if you take 100 Gauss field, you dissipate it, what you get is something like maybe 10 keV or a few tens of keV per particle. So in my view, this would be called plasma heating as a result of reconnection. Non-thermal particle acceleration we talk about is the fact that we produce electrons to hundreds of kilo-electron volts and protons to mega-electron volts and so forth. All right. Now, in astrophysics, there are a number of processes that have traditionally been discussed in the context of particle acceleration. They include shocks, which tap into the bulk kinetic energy of large-scale flow. Magnetic reconnection, this is what we're talking about here, which are powered by magnetic energy dissipation. And there is turbulent particle acceleration due to small-scale kinetic and magnetic energy. However, in addition to mechanisms, systems, perhaps direct electric field acceleration in pulsar magnetospheres that John Arons knows everything about. I think we can talk to him. OK, now, having defined what we mean by non-thermal particle acceleration, we can talk about certain examples of where this happens in the universe. And there are a few examples that I'm going to discuss now very briefly. And I think all of them, well, that magnetic reconnection has been invoked to explain particle acceleration as perhaps a competing mechanism with, say, shocks in each one of them, except perhaps for this first one. At least I'm not aware of reconnection models of producing cosmic ray spectrums. But cosmic ray spectrum, of course, is the most famous example of non-thermal particle acceleration in the universe. Then there are closer to home solar and stellar flares that Jim Drake has talked about, producing hard X-rays, accelerating both electrons and protons to very high energies, and producing power law spectra. Perhaps similar processes may happen in, so this happens in the solar corona. Perhaps similar processes may also happen in other astrophysical coronae, for example, in accreting black holes, such as Cygnus X1, where we do observe also power law tails at high energies in hard X-rays. And then if you move out from the black hole, then we see signatures of non-thermal particle acceleration in AGN and in particular blazar jets at distances that are very, very far from the central engines, which implies in situ particle acceleration. And one of the most famous examples of this, or the most challenging to understand, is TeV flares that are observed in blazars that have very rapid time variability, time scale of order minutes. And they involve, well, presumably electrons producing TeV, photons, which is really remarkable. Okay. Particle acceleration perhaps also happens in gamma ray bursts in the prompt emission. This is a kind of typical canonical spectrum of what we believe that gamma ray bursts produce. As you can see, it's characterized by two power laws. So the implication of this is that there is an underlying power law distributions of electrons in the photons. So non-thermal emission. In the case of gamma ray pulsars, such as the crab, there is also an indication of very high energy. There is hundreds of GeV pulsed emission. The word pulsed here is important because it means that the emission presumably occurs somewhere not very far from the, say, light cylinder of the pulsar. So in the inner part of the system, where there is a power law extending to hundreds of GeV. And further out from the pulsar, in the pulsar wind nebula, there is also a non-pulsed emission in gamma rays. There are flares that Neil Garros talked about. These are very puzzling and very interesting because they presumably, they're detected at up to GeV energies, and they're presumably produced as synchrotron emission by peta-electron volt, 10 to the 15 electron volt electrons. And it's a challenge to explain how these come about. Okay. One remark I would like to make here is that, again, except for the first example that I gave, except for cosmic rays, in all these other systems, we infer the presence of non-thermal particle acceleration, not directly, not because we can measure particles, as we would in the Earth magnetosphere, for example, but by the emission these particles produce. That is, by photons that we detect here at Earth. And this is an important point, as I will come back later. Okay. Now, when we talk about particle acceleration, we talk about distribution function, right? We can say that instead of Maxwellian, we have a power law. So our language necessarily requires kinetic description. We talk about not fluid quantities, but kinetic quantities. And if you want to study these processes numerically, the tool of choice is a particle and cell simulations, or PIC simulations. Okay? And there has been, indeed, a large number of studies of magnetic particle acceleration in both relativistic and non-relativistic contexts. And there are many open questions still remaining. It's a very active area of research. In particular, the questions of what the spectra really are I think is not quite settled, although perhaps Jim may disagree with me. All right. Now, but I'm not going to discuss that very much. I would like to turn to the question of what may limit the maximum energy that particles can achieve. So let's say if we do talk about non-thermal particle acceleration, right? And let's say we use as a signature with the presence of a non-thermal, of a power law tail of particles. The power law eventually cuts off, maybe exponentially, but at some high energy it cuts off. The question is what determines the energy at which it cuts off? Well, there are several processes that can produce such a limit. One of them is just the maximum electric potential that produces the acceleration in the first place. After all, acceleration of particles is done ultimately by electric field, not by magnetic field, of course, but energy can only be increased by the electric field. And so there is, one can just define a simple limit equal to the electron charge times reconnection electric field times the system size. A similar process can also be defined in terms of finite time of acceleration, right? If the particles spend only so much time within the active acceleration region with a certain electric field, then there is only some maximum energy they can get to. And this limit is what some people call extreme acceleration. It's actually a very high limit usually. The electric field here can be related to the magnetic field, the reconnecting magnetic field. And usually, as Jim explained, it's about, say 1/10 of the magnetic field times VA over C. In the case of relativistic reconnection, which is of interest for highest energy particles, VA is of order C. Okay. So it basically means that the maximum energy per particle is just a product of magnetic field times the length of the system, more or less. It scales with it, at least. The same condition can also be understood in terms of the Larmor radius of particles. It means that the Larmor radius of particles becomes comparable to the system size. Right. So that's one limitation on the maximum particle energy. Another one that becomes important in various astrophysical contexts, in various astrophysical environments, that is usually not important at all in more familiar reconnecting systems such as solar flares or Earth magnetosphere or in laboratory devices. But it is important in astrophysics, and that is the radiation reaction. If you have a large enough system and strong enough magnetic field, and this limit becomes so large that particles getting accelerated will reach energy levels so high, at least the electrons, that they will start radiating, and at some point, the feedback that the radiation losses exert on the particles will become important. And that introduces another limitation. Basically, the acceleration, we can estimate this by setting the accelerating force, which is just the electric force, equal to the radiative losses, right? Radiation drag force, which is radiative power divided by the velocity of the particle. For example, for the case of synchrotron radiation, setting these two equal to each other, one gets the following estimate for the maximum, say, Lorentz factor that an electron can reach. See, it's cast in terms of electric field and magnetic field. And interestingly, if we then 3 minutes, okay. Is it really? All right. Are you sure? I'm going to start negotiating here. All right. Well, anyway, so if we then take this expression for the maximum energy and plug it in the expression for the synchrotron photon energy, remember, this is synchrotron reaction, one gets the maximum energy that synchrotron photons can have, and that's a fundamental constant, actually around 100 MeV. Right. And once again, it's important for certain things like the Crab nebula. Now, well, this last topic that I discussed, that is, radiation, makes it imperative to study the effects of radiation on reconnection and on particle acceleration in reconnection in particular. In conventional reconnection studies, radiation is not included, simply because it's not important on the time scales of the process. However, in many astrophysical situations, the energy density is high enough and the system size that radiation may affect the reconnection process itself. It may affect particle acceleration, especially. Examples of this include, Crab nebula flares, that Neil talked about, where indeed we are pushing the synchrotron radiation reaction becomes important for the particles that, PeV particles that emit these GeV photons. However, if you move closer to the pulsar itself, we get into like the pulsar magnetosphere and study reconnection. In that context, the magnetic field there is much, much stronger, of course. And it's so strong that synchrotron cooling affects not only highest energy particles, but all particles. So in that case, reconnection occurs in this strong cooling regime, where radiation has to be taken into account. In addition, radiation is our only observational probe into many examples of astrophysical systems where we think reconnection happens. And so in order to connect our theories or simulations with observations, we really have to understand how reconnection layer looks like, literally. Right? What are these radiative signatures? What is the photon spectrum, the light curve, and so forth? And in order to investigate this, we, at Colorado, we developed a new radiative peak code. It was developed by my postdoc, Benoit Cerruti. It's basically a regular peak code, electromagnetic, relativistic, but it includes also radiation reaction force due to synchrotron radiation or inverse Compton radiation. And we applied this to the reconnection problem. OK, a movie that you cannot see, of course, right? Let me just, but this movie would not be very different from any of the movies that well, Jim didn't show any movies, right? But the images from the movies that he showed, for example. The reconnection process is still the same. Snapshots, right. Now, however, let me tell you about the key new results we obtained from these studies. That simulation, in contrast with other previous simulations, includes radiation reaction on the particles, and it also calculates the observable radiative signatures. Right? So let me tell you what we found. First of all, we found that the highest energy particles are not isotropically distributed in space. There is a very important effect here that we call kinetic beaming, which is a strong energy-dependent anisotropy of highest energy particles. So this map here shows directions of particles with the reconnection layer direction being in this midplane. So it's kind of similar to galactic maps. 1 minute, OK. And what you see here is that the most energetic particles are not flying around in all directions, but they're beamed in a few discrete, relatively narrow beams, shown here. And these beams sweep around from side to side, which creates very rapid variability for any observers looking at a given direction. And also, if the observer happens to intersect the beam, then the radiation, the highest energy spectrum, will be highly enhanced, which is this box number 1. And if the observer looks from this direction, it will be suppressed. And overall, this picture can be described in terms of the beaming angle of particles or radiation, omega, as function of the energy of the particles, for example. You can see that it's mostly isotropic for low energy particles, but then becomes very narrow beam for highest energy particles. And this has tremendous implications for our ability to connect with observations, simulations with observations, or to infer physical properties of the system from observations. We also applied this to the problem of gamma ray flares, producing, trying to explain this emission of synchrotron photons in excess of the classical limit that I discussed. So this is my last slide. In lieu of conclusions, I'll just list a few things that I think should be and could be done in the next 10 years in this field. Yeah, I got the mic.
Very interesting.
It's
question from effects of radiation reaction on the behavior of these
reconnecting systems is whether the particles running away to the radiation reaction limit are a small fraction at the tail of distribution, or whether the whole collection of particles which contribute to the current in the reconnection flow are running away. It's really important to the question of the efficiency out.
Right.
You know, most of these, in a way, this comment or question is addressed to Jim also. The reconnection layer is typically rather thin. If you do it formally, it's down on microscopic lengths, skin depths. It can be hard to get enough particles to actually experience this field to produce the radiation you see. in the simulations you guys just put out a few months ago, it seems that only a small fraction of the particles ran away and hit the radiation reaction limit, and most of the current that was flowing in the reconnection layer did not experience this. Do you have any feeling for what determines whether the bulk of the currents in a reconnection flow, or more generally, you'd like to ask the question more generally, but stick to reconnection, that you can get runaway to the radiation limit, because it's a major issue for the efficiency of what it is you're going to see. And as you say, you see only the radiation out. You know,
right.
Like, we really want to know
what
want to know what the energy input is to do this, and it makes
right.
a big difference of whether it was an inefficient or an efficient accelerator.
Well, that's an excellent question, so thank you, John. One thing is, let's say in the case of crab flares, the synchrotron radiation reaction becomes important only for these PeV particles, whereas the bulk of particles are, say, 10 to the 6, Lorentz factor of 10 to the 6, or 3 orders of magnitude lower, perhaps. For them, radiation reaction is not important, and they presumably carry most of the current and determine the dynamics. However, there are other situations where this may not be the case, and I think it has to do a lot with, let's say, the strength of the field, or, well, in a certain way. In particular, the strength of the synchrotron cooling you would get for typical particles comprising the reconnection layer. So just to give you an example, in the case of, again, crab pulsar wind nebula flares, the field is about 1 milligauss. It's relatively weak. If you go all the way to the light cylinder, the field is 1 megagauss. And in that case, if you just estimate what the typical particles are, you'll find that synchrotron cooling is very important for all of them. So presumably in that case, well, the situation is completely changed because of this. So it's basically, if you can take, again, let's do this. We can, as a first cut, it's basically a comparison of two numbers, right? One number is you take the typical temperature you would expect in a reconnection layer. By taking magnetic field energy that is available, dividing it by the number of particles, you get typical temperature. As in the case of the solar flares, that could be 10 keV, for example. And then you compare that energy with this estimate for the that I had there for the radiation reaction limit, right? This one. So typically, you probably find that this radiation reaction limited energy is much, much higher than the typical temperature. Then only a few particles on the tail are experiencing this. But again, there are situations, high energy density systems in astrophysics, where they become comparable. And then you cannot neglect radiation at all. Yeah, thanks.